Okay, so chapter 7 is all about oblique triangles and all these different laws of sines, laws of cosines, vectors, that kind of stuff. So this is going to touch back to a lot of geometry. If you had geometry in high school, hopefully some of this is going to seem pretty familiar, maybe in a distant fashion. All semester long, we've talked about triangles, we've talked about angles, we've talked about all of that kind of stuff, but we've been pretty specific in using right triangles for like everything. So today we're going to start talking about what happens with all these other triangles that aren't right triangles. And so congruent triangles is a lot of times what we end up talking about. We're comparing two different triangles, and that means that their corresponding sides and their corresponding angles are equal. Only then can we say that they are congruent. If they have like the same angles, but their sizes are different, so we have an itty bitty triangle that looks the same shape as a really big triangle, then those are similar triangles. That's different than congruent. When we talk about congruent triangles, we actually have a lot of congruent axioms, and these are where maybe some of this is going to start flashing back a little bit from geometry, because you do cover all of these different congruencies back in geometry. You have side angle side, which means if you know the side length, the angle, and then the side length, where that angle falls between those two different side lengths, then you can say that those are congruent. We can solve a triangle if we know angle, side, angle. If we know all the side lengths, we can figure it out. Or if we know side, angle, angle. The reason why side angle angle works, there's a little star there, is that the third angle can be found because we know all the angles of a triangle have to add up to 180. So we can find that third angle, and then we can actually apply our angle side angle axiom to compare our triangles. And yes, I made a really lame math joke. Bless you. To where an oblique triangle is not a right triangle, aka it's a wrong triangle. It was late when I made notes. So it is what it is. But, I mean, in all reality, an oblique triangle, at its most basic definition, is not a right triangle. These are acute triangles. These are obtuse triangles. They just don't have a right angle in them. And so we can't apply all of the stuff that we've been learning about throughout the semester. So we have to use these different axioms to come up with our side lengths and our angles and all that kind of stuff. Under our congruence axioms, you'll note that we do have like a side, side, side axiom, but we don't have an angle, angle, angle axiom. And the reason why is because angle, angle, angle will only guarantee similarity, but not congruence. And that's because if you have an equilateral triangle, or an equiangular triangle, I guess you would consider it, where it looks like, you can't see, looks like this, where everything is 60 degrees, all the angles are 60 degrees. That triangle has 60 degrees everywhere, but so does this triangle. And those are not the same triangle at all. One's tiny, one's big. So we can't say they are congruent, because in order to be congruent, the sides have to match up and the angles have to match up. And that's why angle, angle, angle only guarantees similarity and not congruence. And if you happen to look at the pictures up here, all the little tick marks and the little half circles, those correlate between the two different triangles, so that the side that has two tick marks on the first triangle, side B, correlates or is congruent to the side Y on the second one, and so on and so forth. That's how we make those similarities, and we mark them. What we're going to be doing this entire chapter, and especially in these first couple of sections, is we're going to be solving triangles. When you solve a triangle, what you're doing is you are having to find all of the angles and you're having to find all of the side lengths. That's what it means to solve a triangle. So if you are asked on a problem to solve a triangle and you're only given half of that information, you're going to be expected to find the other half. Sometimes you are going to just be asked for a specific side length or the measure of a specific angle, but most of the time you're going to be asked to find all of it. So just note, if it says solve a triangle, you have to know all 3 side lengths and all 3 angles. And so how do we do that when it's not a right triangle? Well, we're going to use our law of sines. That's a new law that you're going to have moving forward, where if you have any triangle whatsoever and you know the side lengths, then A over sine A is equal to B over sine B, which is equal to C over sine C, where the capital A, B, and C are the angles within your triangle. For these problems, they have to give you some of the information. They'll have to give you some of the side lengths or some of the angles, and you'll have to come up with the other measures. But this law of sines is going to be crucial as we move forward in this chapter. And note that if you put A over sine A, that's the same thing as putting sine A over A. It doesn't really matter if you flip-flop those as long as you flip-flop the entire thing. So I can't say sine A over A is equal to B over sine B. I can't do that. But I can flip the entire thing if I want to put my sines on top and my lengths on bottom. I think I'm pretty consistent, and I usually put the sines on in the denominator. Your book kind of flip-flops back and forth. So they'll give us a lot of the tools, they'll give us a lot of the pieces, and then we're going to use this specifically, and we are also going to use the fact that all of our interior angles add up to 180. We're going to use that in order to come up with our other angles a lot of times. If you liked geometry, I think you'll really like this chapter. If you didn't like geometry, the semester's almost over. That's about what I got. It's not long. Are you ready to try one? Okay. Let's try and solve triangle. I might have to zoom out a little bit. We're going to solve triangle ABC. If A is 32 degrees, B is 81.8 degrees, and A is 42.9 centimeters. If you are a visual person, you are more than welcome to draw these. You are not required to draw these, or at least most of them you won't need to draw in order to do them. But sometimes it's nice to have a labeled picture to get going with on this stuff. Angle A is 32 degrees, it tells us. Angle B is 81.8 degrees. Side A falls opposite of angle A. It's 42.9 centimeters. And so what we don't know is we don't know side B, we don't know angle C, and we don't know side C. Those are the 3 different components that we are missing as of right now for our triangle. What we do have is we have angle, angle, side, or side, angle, angle, however you want to think about it. That was the last of our congruence axioms, and that's the one where we will have to find our third angle, and then we can apply our sine, our law of sines and stuff like that moving forward. So whenever you are asked to solve a triangle, If you are only missing one of the angles, that's usually the easiest place to start. That's always where I would start because that's pretty basic algebra, where we have A plus B plus C equals 180. So if A is 32 degrees and B is 81.8 degrees, then I can subtract those both over and find that C is 66.2 degrees. So now I know all my angles, and I'm just missing side B and side C. Notice they gave me side A and they gave me angle A. So whenever I go to find side B and side C, I'm going to use that information because that's given information. It doesn't require me to compute anything, and it also takes a lot of the error out, because if I use angle C and side C later on, if I were to know that, there's still some room for error that maybe I messed up and I copied something wrong. So what I mean by that is I need to figure out what B is and I need to figure out what C is. Well, based on my law of sines, I know that A over sine A equals B over sine B. I don't have to have the C over sine C at this point. I can use whichever of the fractions or the comparisons that I want to use. Since I know A and I know angle A and I know angle B, the only thing I would be missing out of this would be the side length of B. So I can use this and solve for B. A is 42.9. Sine of A is 32 equals B over sine of B, which is 81.8. Just like in previous sections, don't type in sine 32 and then get the decimal and put the decimal on your paper, because the more times you round, the further away from the true answer you are getting. So try not to do any of that kind of stuff until the very end. On your homework today, I noticed when I made it just a little bit ago, it even tells you in the specific answers, don't round until the last step. So the longer you can keep things written as sine of whatever it is, the better your answer is going to be. So how do I solve in algebra? How do I solve if I have a fraction equal to a fraction? Cross multiply, or you can also think about just multiplying this sine of 81.8 over, however you like to think about it, totally works. If I multiply that sine of 81.8 over, then I'll get 42.9 sine 81.8 all over sine of 32. So I type that big bad boy in, and I get that B is approximately 80.1 centimeters. And on your homework and your quiz, it tells you exactly how many decimal places to round to every single time. I looked to make sure. So now we do almost the exact same process, but we're going to do it with C. Because we can use the A over A. A over sine A equals C over sine C. We found C just a few minutes ago with 66.2, so then the only part we would be missing in that would be our lower C, the actual side length. So 42.9 over sine 32 equals C over sine of 66.2. So sine is, or C, excuse me, is 74.1 centimeters. So we used the information they gave us, we were able to find our third angle, and then after that we just used different components of our law of sines in order to find the different side lengths. I don't think these problems are too horrible. I don't know. What about you guys? Okay. I kind of liked them. I thought it was kind of a breath of fresh air after some of the other stuff. Are there any questions at all on how we did any aspect of this problem? Okay, let's look at a couple word problems then. Word problems don't necessarily make them harder, it just makes them different. If you don't want to write down all the words, I totally get it. These are examples straight out of your book, out of the lecture portion. So if you wanted to look at them there, you could. This one is about a river. It says an engineer wishes to measure the distance across a river. He determines that C is 112.90 degrees, A is 31.10 degrees, and B measures 347.6 feet. We need to find A, because A is given as the distance across the actual river, which is what he could not measure. Why? I don't know. He can measure all this other stuff, though. So B measures 36. C measures at 112. We know that this side length over here measures 347.6. So we are given angle A. No, we're not. Yes, we are. We're given angle A and we're given angle C. And I kind of ruined it. We're going to have to find angle B. How do we find angle B? Yeah. We can do 180 degrees minus A minus C, and that'll tell us B. The other way to think about that is A plus B plus C equals 180. So we'd have 180 minus A, which they said is 31.10, minus C, which is 112.90, and that'll give us our B. So B is 36. The reason why we want to find B is because the side length of our triangle that they told us is the one opposite of angle B. That means we know side B. And if we know side B, we need to know angle B so we can use our law of sines. Because law of sines is B over sine B. And we're trying to find A, but we know what angle A is. So that's why we went ahead and found our angle B first so that we could apply it. We already knew angle C, but we don't know side C, and so that's why we went ahead and found the angle B. So B is 347.6, and then we have sine of 36 equals A over sine of 31.10. $347.6 sine 31.10. We're going to round to 1 decimal place for this one. How wide is the river? $305.5 feet, exactly. $305.5. questions? Oh no. Here we go. Okay, if there's not questions, we're going to do a bearings one. Remember, bearings we covered back in 2.5, so it's been a minute. With the bearing problems, a lot of times we talked about ships, and they would set off on different bearings, or we would talk about like radio towers and stations like that, which is what we're going to talk about here. Remember, what made bearings different than our traditional angles that we were used to talking about is that we didn't start from like our x-axis and move counterclockwise. We started from a north position, and then depending on how the bearings were given, we went east and west off of that. And so if you need a refresher on bearings, that's in 2.5. But here's the problem. It says 2 ranger stations are on an east-west line 110 miles apart. Okay, an east-west line runs horizontally. You can't see that. Runs horizontally. That's an east-west line. It runs east and west. So we have a station here, we have a station here, and it tells us that those are 110 miles apart. A forest fire is located at a bearing of north 42 degrees east from the western station at A. So this is western station, this is eastern station. So if we are doing bearings, you're going to want to draw in your north-south lines. 42 degrees east, so north 42 degrees east from A. That's where we go this direction. 42 degrees. So I'm going to put my fire. I have red. I can make an actual fire. Here's my fire. And right here is 42 degrees. Because it comes off of your north-south line. Bearings come off of there. And I'm pretty sure I have a typo in my notes. Or no, I don't. I didn't draw my fire at the right spot. My fire needs to be over here. The reason why I know my fire is in the wrong spot is because it tells me that my bearing from station B, which is the eastern station, is north 15 degrees east. 15 degrees east is going to put it this side. And that's because I'm not getting a right triangle, I'm getting an oblique triangle, which means I need to have my fire way further over here on the right-hand side of my north-south line for my B station. Previously in 2.5, we would always have it over here because it would end up making a nice right triangle and we were able to go from there. But we aren't dealing with right triangles, we're dealing with oblique triangles, and so my fire actually needs to be over here. I have a really nice picture of my stations here. I say nice, my fire looks pretty wonky. But I have my station A, my station B. I have my 42 degrees, I have my 15 degrees. They're 110 miles apart. That's all the information they've given us so far. It says to the nearest 10 miles, how far is the fire away from the western station? The western station is over here. That's station A. So I need to know this long side right here, which is actually side B, because that's opposite of angle B. So I'm trying to find side B based on all of this information. Well, they didn't give me any of my angles, so how do I do this? Yeah. Our north-south lines end up making right triangles with our east-west ground as it would be here. So finding angle A over here is going to be 90 minus 42. Finding angle B over here is going to be 90 plus the 15. And so then I'm able to find those. And if I have those, I can come up with this other one, which is C, which is across from here. I can find all of my angles because I used bearing and because they gave me my bearing directions of where the fire was located from my different stations. So angle A is over here at station A. I did 90 minus 42, which tells me it's 48 degrees. Measure of angle B, which is station B, will be the 90 plus. And then I can find my third angle by taking 180 minus those other two. So this one's 27, 105, 48. And I know this is C, B, A. This is 110. So I rewrote my triangle just to make it a little less confusing in that I don't have my stations, I don't have my fire, I don't have my bearings, I don't have any of that kind of stuff. But I wanted to know the distance to the nearest 10 miles from how far away the fire is from station A. So that means I need to know side B. I know angle C, I know side C, so I'm going to use C over sine C equals B over sine B. I'm going to use that part of my law of sines. Type all that into your calculator and you get they are 230 miles apart. We could have done the same thing, or we could continue and figure out how far away the fire is from station B if it had asked us to, but it didn't. Are there questions on either of these problems, the river problem or the bearing problem? Okay. If there's no questions, that's using the law of sines. We have one more topic we're going to talk about in this section, and it's area. Finding the area of these oblique triangles. The area of a triangle, way back in geometry, very basic format, is a funky A, which is why it looks all cursive and stuff like that. A funky A equals 1/2 base times height. The base of your triangle times the height of your triangle. But a lot of times we're not going to know all that information. But we can use the side angle side congruency to find the area of a triangle using our sines. To where the angle of, or excuse me, the area of a triangle is 1/2 BC times sine A, or 1/2 AB times sine C, or 1/2 AC times sine B. For these, you have two sides, and then you have sine of the side that you don't know, is what it comes down to. So to find the area of a triangle, of one of these oblique triangles using side angle side, you know two of the sides, and you're going to take those times 1/2 times sine of the angle you do know. Just writing those up there so I can move this. We are going to find the area of this triangle. Find the area of the given triangle. So we know side A is 34 feet. We know angle B is 55 degrees 10 minutes. And we know that side C is 42 feet. So we know side, angle, side. So we can use our areas that we just saw. Now, which one do we use? Well, what angle do we know? We know angle B. So we want to use the one that has the angle B. One half AC sine B. 1/2 A is 34 feet, C is 42 feet, and then we would do sine of 55 degrees 10 minutes. Now, you're going to have to convert from minutes into degrees. We did that a long time ago. Who remembers how we do that? How many minutes are in a degree? 60. So if we need to do some converting, what we do is we take the 55 degrees and we add, it says 10 minutes, so it's 10 minutes over 60 minutes will give us our proportional degree, which is like 0.166666 forever, ever, ever. So put a couple of those out there to where this is, 55.16667, like that. And you'll get pretty close, especially because these are going to ask you to round to the nearest foot or 1 decimal place or 2 decimal places. For this one, we're going to round to the nearest squared feet, which is 586 square feet. These are pretty much always plug and chug style problems. The only way that they might not be is if they don't give you the correct side and angles, and you're going to have to come up with some of the other sides and angles. But the way that we come up with our sides and angles are just like what we've been doing, where the interior angles add up to 180 degrees, or we use our law of sines in order to come up with some of our other side lengths. Are there questions on this one? Okay, we got one more. This one's going to have us do a little bit more to it, just because they don't give us the right information. We need to find the area of this triangle. Angle A is 24 degrees 40 minutes. Side B is 27.3 centimeters, and angle C is 52 degrees 40 minutes. When we find the area of a triangle, we have to have side angle side. But we don't have side angle side. We have angle side angle. We have an angle, a side, and an angle. So we don't have the right information. So we're going to have to come up with some of the other information. Bless you. We need to come up with side C, or we need to come up with side A. We've got to come up with something. I know 2 of my angles, so I'm going to go ahead and come up with angle B, so that way I know that information. Angle B will be 180 degrees minus 52 degrees 40 minutes minus 24 degrees 40 minutes. Again, you'll have to convert. Actually, I didn't convert. I left it. I converted later. So leave it. You can subtract using minutes. Just remember, if you end up with something that's over 60 minutes, that means you have an extra degree. It's 180 minus 77 degrees, 20 minutes. So B is 102 degrees, 40 minutes. The reason why I didn't is because later on we're going to do something with our signs. And the longer we hold out, remember with the rounding, the better our answer is going to be. I will say, on looking at the Pearson site, though, it is nice in that they give you a window or a leeway of so many percentage points and things like that, to where if it's 102.2, it'll have a grace period of 0.1 or 0.2, and so if you're close to it, because it knows that you are rounding at various points in the problem, it does go ahead and give you credit. I thought that was really neat when I was looking at that today. So now we know what B is, 102.40, but I still don't have side angle side, so I need to come up with one of my other sides. I need to come up here and do side angle side, or I need to come up with here and do side angle side. Either way would be fine. I ended up finding side A, which is over here. So to find your side, you're going to have to use your law of sines. And I did B over B because I don't know what side C is. Sine is 24 degrees 40 minutes. B we have is 27.3. And we just found that it is 102, not 120, 102 degrees 40 minutes. $27.3 sine. I went ahead and converted at this point. Now that I have a second side length, I found what side A is, I can actually find the area of my triangle. That's what we've been trying to do. We've been trying to find the area, but we didn't have the right information. We needed to have a side angle side, and now we finally do. We have side angle side. What angle do we have that we're using? If we're using side angle side, we're using angle C. So we want to use this one where we have sine of C, because that's the angle we're going to use. So while we know all of our other angles, the one we're actually using in this case is C. So we're going to take 1/2 times side A, which we just found was 11.7, side B, which is 27.3, sine of 52 degrees 40 minutes, which is 52.667. We're going to round to the nearest square centimeter for this one. hopefully you get 127 square centimeters is the area of that actual triangle.